Okay. So let's pick up where we left off. Let's see, we should have our Ann Arbor person joining, or not our Ann Arbor, Irvine person joining us today. I don't see them online. Maybe they have the wrong time zone. Yeah. Okay, so picking up where we left off, we were talking about the various things that an operating system provides us. So again, this idea of the operating system sits between us and the hardware to allow a computer to be more easily controlled by a human being. And the mechanisms by which it does that is by providing us all these different services. Okay, so IO stuff, driver support, we talked about that, where in older operating systems, when the operating system shipped, it had to have all the hardware it was ever going to support built into it. Now we've created a kind of a modular driver system that allows you to create a driver to teach it how to talk to a piece of hardware that came out 7 months after the operating system shipped, that kind of stuff. Big thing is going to be process management. We're going to spend a lot of the semester talking about process management and inter-process communication. So making different processes talk to each other. And there's kind of two different levels there of processes talking to each other. So a process is like a program running on the computer. So one level is if you have two different user programs, maybe you've written two programs and you've launched both of them, how do they talk to each other? And then secondarily, if you have a process that wants to talk to a process that's running as the root user, it's running with different permissions and it's actually running at a different part of memory, a protected part of memory. So we have specific mechanisms to allow you to communicate with secure processes that are running, because they won't just allow you to, like when you think about when you first learned about pointers and like C and C++, one of the, kind of with great power comes great responsibility. So one of the downsides of having access to a memory address and being able to just walk off the end of an array and start messing around in memory, one of the downsides is that you potentially can corrupt something in memory. All right, and you've probably read about all sorts of different hacks dealing with like buffer overflow errors and stuff like that, where you are effectively writing something past the end of a memory data structure, and that has an impact on the underlying operating system. Well, with that in mind, modern day operating systems let administrative programs run in a protected memory space. That is memory space whose memory addresses are mapped differently than the memory addresses on the user side. So not only are they secure, it's not like you have a bunch of user space followed by administrator space and it's just one memory address over. It's a whole different mapping of that memory with security protocols in place. So there has to be some way to allow a user process to talk to a administrator process in the event that they might need to talk to each other. Another thing that the operating system provides is processor management, CPU management. This kind of goes hand in hand with our process management. So processes are running programs on your computer, and many times processes are broken down into multiple sub-processes that are also running. More modernly, a lot of these are represented as multi-threaded applications. We'll talk about that as well. But at the end of the day, one of the jobs of the operating system is to take all those processes that are currently trying to run on the computer at the same time and figure out how can we schedule them for running on the CPU or the multiple cores. If you have multiple CPUs on a machine, how do we schedule them so everything can get done as fast as possible, and ultimately we fake out the end user and they think that they're getting super fast response time even if things aren't technically happening at the same time more than the number of cores you have. All right, so probably most of our time is going to be spent in this world of process management and also CPU management to a lesser degree, because that's something that we can't really manipulate. You know, we're kind of at the mercy of when our processes are getting CPU time. But we do have to then take into consideration the idea of, hey, I might try to talk to a process that currently is not on the CPU, so there could be some sort of delay where I need to wait for some sort of feedback that they got my message, something like that. We might need to build protocols for, you know, communicating with other processes so that we become notified that something has occurred. Operating systems also provide file systems. So, you know, this is something that it's kind of interesting. It's something that's probably we're less and less aware of as modern computer users, because now we pretty much just, you know, double click on something and we see a folder and we don't really think about the organization, you know, of that. So if I go into a Unix terminal, so this is a POSIX-based operating system, and if I was actually on Linux, it would look similar to this. So, you know, when I go to the root directory, which would be kind of equivalent to the C directory if you're on a Windows machine. So what's the default file system on Windows these days? If you were to format an external USB drive or a jump drive on Windows, how would you format it? Go ahead. It has a name, and all of you have seen the name. When you first buy an external hard drive, or you have a little USB stick, if you plug it into a PC, it works. You plug it into a Mac, it also works, right? So whatever file system it's running is understandable by both of those operating systems, right? Okay, so the default file system that's running on a jump drive is typically FAT32. Okay, so it's a 32-bit file allocation table is what that file system is called. Now, Windows, you install Windows 11 on your machine today, it's actually running a different file system than that. Now, the reason that the jump drives are not formatted with that different file system is because we want them to be compatible on Mac and PC, as well as, you know, Unix systems. And Microsoft, anybody know what Microsoft's file system these days is called? Not FAT32, but it's called NTFS. Okay, so we talked about the NT kernel. So just like their new technology kernel, we have the new technology file system. Been around for a long, long time, but that's a proprietary file system. So there are programs on the Mac that will allow you to read an NTFS file system, but writing to it can be somewhat problematic and experimental. They exist, but it's not a very reliable situation. Same thing on Unix. So generally speaking, if you have a jump drive that you want to be able to move between different operating systems, you format it, comes pre-formatted, FAT32, so that it'll work on all those different computers, because all those different operating systems know how to read and write to the FAT32 file system. All right, so the idea here is that one of these services an operating system provides is a file system itself, that is the file system provided by the operating system. Okay, so here on the Mac, I'm running a version of the Unix file system. If I go into disk utility here, it's running APFS, which is a version of the Unix file system. It used to be UFS on older versions of the Mac OS. Okay, but a different file system than FAT32, a different file system than NTFS, but ultimately they're accomplishing the same things. When we think about a file system, what are they doing? They're giving us the ability to create files. They're giving us the ability to probably create folders and put files in folders, right? They're giving us the ability to, you know, move around within the file system. So typically when we think about file systems, we're thinking about some sort of hierarchy of files and directories. And that's pretty much a truth of all file systems. You know, on Linux and Unix, the base directory is the / directory. Okay, if you're on a Windows machine, what's your top level directory called? C drive, right? Double click on C, that shows you here's the top level. We can't go any higher than this. This is the top of the hierarchy for your file system. It's effectively the same crap, right? It's the top level you have. Inside there, you have a hierarchy. If you open up the C drive on a Windows machine, you're going to see a whole bunch of folders in there, some of which you're going to recognize. You kind of have like your System 32, System 64 stuff. So there's some core stuff, and then you have things that maybe have been software applications that you've installed. So some of them are kind of common to all Windows-based operating systems these days, and some of them are things that have been created, folders and files that have been created by third-party applications you've installed onto your computer. Similarly here, if we look at this / directory, bin, dev, etc, home, opt, sbin, temp, user, var. These are folders that you will see on all POSIX-based operating systems, all Linux or Unix-based operating systems. We'll talk about what POSIX means later on. So it's kind of a POSIX-compatible operating system. So there's kind of a known format that that they use. But now notice here that Apple has tossed in a couple of folders that come core with the operating system. They have a folder called applications, very similar to Microsoft has a folder where all your 32 and 64-bit applications live. There's a library folder, there's a system folder, users, volumes. So these are things that are more unique to the Macintosh operating system, but it's built on top of a file system that supports the creation of files, and supports the creation of folders. And files have different permissions associated with them. So if I actually, let's just go into maybe etc. So if I go into the etc directory, these are a whole bunch of files that live in here. A lot of them are configuration files. Anything with a .conf on it is a configuration file. Some of these are executable things. Over here to the left, these are the permissions. So this is the permission for the owner, the permission for the group, and the permissions for everybody else. So if you're the person who created this guy, the owner is root, you can read and write this file. But if you're in the group called wheel, you can read it. And if you're anybody else, you can read it. So you can't change it. Ones that have an X on the end of it, those are probably applications that can be executed, right? So they can be run. So part of what it is, not just the creation of files and the creation of folders, but it also supports permissions, security around your files and folders and things like that. Okay, so file systems allow us to do a whole bunch of different stuff. And it's one of those things that's kind of out of sight, out of mind. We don't really think about it because it's just always been there. Okay, but it's a pretty important thing of what an operating system provides for us. Okay, so the idea is of what is systems programming? Well, systems programming would be writing our own pieces of software, third-party applications that work with these various services that the operating system provides in the context of whatever problem we're trying to solve. All right, so probably we are trying to solve some sort of, could be a public facing application. It could be that we're writing some kind of server to run on the computer, whatever it is. To call it systems programming probably means that at some level, we are having to talk to the actual operating system from our program because we are reliant on services that the operating system provides, as opposed to maybe applications you've written up to this point where, I mean, you're doing all sorts of different stuff, good logic stuff, but you've never really relied on things that the operating system knows how to do. You've maybe kind of indirectly worked with input and output, right? You've printed crap to the screen, you've read stuff in for the user, but those are usually tools that modern day programming languages provide for you, and then they talk to the operating system on your behalf under the hood. So systems programming would kind of be whatever you're writing code and you're specifically talking to the operating system or talking to other processes or working with the file system on the computer. So we'll call this guy any program that directly communicates with one of the services the OS provides or other applications running on the OS. Something along those lines. That's when it would fall into the category of systems programming. But it's just programming, right? We're just using some libraries that we might not commonly use otherwise. All right, what's an API? What can you tell me about this guy? Go ahead. Okay, so that's what it stands for. What is it?
So if the weather channel has a bunch of weather data, such as on they create this interface, which can be programmatically accessed.
Okay, so a good example. So you said if you got the thing like the Weather Channel, and they want to make it so that people like us can write software that maybe we say, hey, I want to know what the current temperature is in Mequon. So maybe what they do is they provide an application programming interface. They provide some sort of piece of software that is waiting for us to connect to, that maybe we have to authenticate with it. Maybe for certain information, they'll just give it to us. Probably this is something they would just give to us. Maybe we say, hey, current temperature, so weatherchannel.com/API/current temperature, and then we hand it maybe a zip code, 53097 for Mequon. And it'll spit back probably a JSON string with a bunch of crap in it, including, current temperature, today's high and low, maybe sunrise, sunset, kind of that public general weathery information. All right. So a place like weather.com that I'm sure has a whole bunch of meteorologists and crap like that working for them, they effectively control a bunch of data, right? Some of that data is for their eyes only. So that's private data. Other data they've made accessible to external users or to other applications. Maybe they're internal applications, but the way you get to that data is not by having it. So if you work for Weather Channel, it's not, if you work for them, you don't want to have 3 different developers. One gets the data directly from the database, another one talks to the API, and maybe another one talks to something else, which then talks to the database. So now you're getting the same information through 3 different mechanisms. A lot of times APIs give you a controlled way at getting data. So even internal applications might still use their normal API with elevated privileges to get the data, so you have a single point where you can control how data flows in and flows out of your system. Okay, so generally, so we'll call this application programming interface. This provides a collection of, typically they're called endpoints, that when called upon give some kind of data or provide a service of some kind. Okay, we can think of it as a little language that lets us talk to pieces of software that we didn't write, and they publish it. Modern day APIs, so if we kind of think about the history of APIs, in the early days, if you were at Weather Channel and you wanted to give external programmers access to your data, you would have written your own little proprietary thing. And, if somebody wanted to have access to it, you'd have to give them, here's the manual of, this is how you talk to our software. Then if, the company next door, they want to have an API, they write their own proprietary thing that has a whole different language for you to talk to their software, and they have to give you a manual. So now when you're writing software, you don't have a standardized way of talking to various pieces of third-party software. So in the early days, everything was proprietary. Then we started to sort of kind of have some standards. One of the early standards was something called SOAP, S-O-A-P. But now all of our APIs are called REST, or sometimes it's RESTful APIs. Any of you ever used a RESTful API? Doing any of your, probably web development type stuff? Okay, can you, what makes an API a RESTful API? This is one of those situations where, like, yeah, I've used it, but I don't know what the heck it is. I don't know what that means. All right, so it's kind of an interesting kind of backstory, I guess. So all of our modern APIs are REST APIs. And the way that we talk to them is that we have a consistent mechanism that you can talk to any RESTful API. All right, you might have certain login credentials for this one versus this one, but the way you pass them, those login credentials would be consistent. The way you say, give me data at this endpoint, that idea is going to be consistent. Pretty much all RESTful APIs today communicate back and forth with JSON, JavaScript object notation. In the early days, it was kind of a halvesy JSON or XML. If you're working with some older APIs, and if it's not broken, don't fix it. You might still be talking XML, but almost all of them now have just converted that to JSON. All right, well, the idea for a RESTful API, let me actually go up. When you think about RESTful APIs, or when you learn about RESTful APIs, sometimes you see this acronym called CRUD. Any of you know what this stands for, besides the obvious? No, so it's an acronym in this case. What can you tell me about that guy? What's HTTP? We've all seen it before, right? Go ahead. Okay, Hypertext Transport Protocol. Okay, that's what it stands for. What is it? Where have you seen it? Where have you seen this guy? Go ahead. Well, the content of a website is HTML. But where have you seen this? Every single one of you in here has seen HTTP before. Where? URL. If you're on a web browser, up there at the top left of the page you're on, it's going to say HTTP. A lot of sites now are HTTPS, which is encrypted HTTP. It's secure. We'll make it so that people can't steal your credit card information, yada, yada, yada. Okay, so this guy stands for Hypertext Transport Protocol. So keep climbing the mountain here. What's a protocol? Like most tech things, we like to use smart sounding words that mean easy things, and then none of us actually knows what it actually means because we are using these crazy. So what does protocol mean? Go ahead. Okay. How many of you know who C3PO is? Okay. Star Wars guy, Star Wars robot, right? The copper guy. And he was a protocol droid, right? What did he do? What was he good at? Go ahead. Translating languages. So a protocol is a language. Right now, we're communicating using the English protocol, right? If you speak another language and you're talking to your friends from who speak the same language, you would be communicating in that protocol. when we're writing our code in here, we're going to be communicating using this C++ protocol. So protocol is a language, okay? Used for communication of some kind. Doesn't really define how complex or simple the language might be. So that's what protocol is. Hypertext transport protocol is probably a language for doing what? Go ahead. Transporting hypertext. So this is a protocol for transporting hypertext. Now, what is hypertext? You already basically answered it before. Hypertext is stuff written in HTML. I'm going to go ahead and say or similar. All right, that's hypertext. Fancy schmancy name for organized data. All right, so we have this protocol that is built for communicating hypertext between two things. All right. Let's go this way. Who speaks HTTP? Besides C3PO, I'm guessing it's programmed in there. Go ahead. Okay, web browser. Web browser speaks HTTP. Who else? At the very least. Go ahead. Computer that's like my computer here that's running the web browser. Okay, so maybe the computer that the web browser is talking to.
Yeah.
Okay, because right now I'm speaking English, right? And if the audience here didn't understand English, we'd have a problem, right? So if I'm the web browser, I'm the web client, and I'm sending requests, I'm saying things using the HTTP protocol, I'm talking to a web server. Okay, what's a web server? When you hear that phrase, a couple connotations should pop into your head. Tell me what you think a web server is.
I feel like it has a collection of websites and URLs.
Okay. Well, on one hand, when we hear the word server, we might think hardware, right? It's a computer somewhere, okay? But it doesn't have to be just a single computer. Depending on, like here on campus, we have a web server, and it's I don't know what our setup is, but it's entirely possible that the same single computer is running our web server as well as our email server, for example. I think our email server is off campus now, but just roll with the example here. All right. So really, from our perspective, when we're talking about a server is a piece of software that listens for incoming connections and deals with them accordingly. So when a web browser talks to a web server, draw a picture here. So here's my web server. So web browser like Chrome or something like that. So is there only one web browser that ever talks to the same web server? Because we have a web server here on campus, right? That hosts the cuw.edu website, right? So can you only get to that with one web browser, one place in the world? Or any one of us with a laptop today right now can open up your web browser of choice and go to that site, right? All right, so we have a whole bunch of these guys. that all have the ability to talk to our web server. All right, so we have a single web server. Go ahead. Why can you access it from other places? Well, that's more of a networking question. It's because the cuw.edu domain lives in the DNS system that's distributed across the country. So this web server has an IP address, a unique thing that's routable. So if we're here on campus and we type in www.cuw.edu, it gets resolved by the DNS server here on campus, and we immediately direct to the local machine. If we're off campus, like in Russia, we type it in, it's going to resolve the IP address of our machine here, which is probably sitting on the what's called an edge router that can accept incoming connections. And because it's coming in on port 80, which is what a web server runs on, typically it'll automatically redirect it to the right IP address for our web server. So that's more of like, how does the internet work type thing. Okay, so multiple web browsers can all talk to a single web server simultaneously, right? We expect that to be a truth. So let's just use the example here. Let's just for the sake of argument, let's say we're going to one of those websites, the portals that have like a whole bunch of news and stuff like that. They take a little bit to load. Okay, and let's say that you're on a really slow internet connection. All right, so you're this guy right here, and you connect to this the main page of the server, which is, let's say it's going to take 5 minutes to load because your internet connection is garbage. Okay, does that mean the rest of these people have to wait until you're done, or can they all do it simultaneously? Well, how? The server is a piece of software, so it's a piece of software running on this computer that sits there and listens for an incoming connection. So let's, this is your machine. So we got that initial incoming connection and it started communicating with you. If you get a phone call and you're talking to somebody, other incoming calls can't get through to you unless you choose to hang up on the person you're currently talking to, right? They don't just join in on the conversation. Go ahead.
Well, I feel like the web server has multiple processes or multiple sections of memory, where what have you, that would allow multiple users to have a slot in the
Okay, well, we're talking about two different things here, though. So you're right. Typically, when we think about a server, that piece of hardware, we're usually talking about something that's, kind of an expensive computer, lots of resources, lots of RAM, lots of processors, yada, yada, yada. So probably has the resources that would be necessary to handle more than one simultaneous connection if that server software was written in the right way. Go ahead. Oh, I missed them. Thank you. Yell out when it happens again. So, whatever. Done deal now. I can't do anything about it. So you're probably right. The actual hardware that server software is running on probably can handle more than one connection at once. In fact, pretty much any hardware can handle more than one. A Raspberry Pi can handle more than one connection at once. But how is it actually accomplishing it? If you pick up if you're on the phone, if I'm on the phone with my mom and some telemarketer calls, they don't get to just take over the phone call. I have to choose to hang up and switch calls, right? I'm busy. That server software is busy. Go ahead.
I'm guessing that what it does is it takes dedicates it switches between each different tier connections to the web browser. Like there's a little bit of CPU time to one, there's a little CPU time to the next.
Okay. So maybe the type thing where
Or if it's like multi-forward, it could have different forwards.
Okay, so like I'm on the phone, another call comes in and, you know, I talk to my mom a little bit, I talk to this next person a little bit, I talk to the next person a little bit, go back and talk to my mom, and just do that really fast, and they all think I'm talking to them in real time. Probably not the way it's gonna work. Go ahead.
Is it like, you pick up the phone and then somebody else calls and you have to hang up the phone, pick up the phone, or is it like this?
Well, you tell me. Usually when I ask a question, I don't get a question in response.
So what do you think about that? That's what I got. I bet you got 2 phones.
Okay,
Or
so the idea here is when this connection comes in, a thread is likely created. And that web browser is handed off to a thread. Now for us here, we can kind of use the idea for this high level discussion, thread and process, we can kind of use interchangeably. Okay, it's a computer program running on the operating system somehow. All right, we'll talk about the somehow part later on, but effectively this single program, the web server, the phone rings, he picks it up, poof, spawns a thread, spawns another process, hands in the phone and says, you take over, hangs up the phone, waits for the next call. Next call comes in, spawns another thread, hands it off, so on and so forth. All right, so they're always connecting to the software program that's running on the web server that's sitting there and listening. Usually it's on port 80 at some IP address. Phone rings, they pick it up, they spawn a child process to go and deal with that communication, to speak HTTP to them, and then they go back and listen. Go ahead. Well, maybe you almost think of like the quarterback. I mean, these guys are still doing logic on behalf of the web server. They're still doing web server stuff. They're just not you could almost think of maybe this top level process as kind of like maybe the secretary that's sitting there taking the incoming calls and transferring it to, you know, the right extension, something like that. So they all have a useful job that's part of the full, you know, solution to the problem. Good. You mean if you chose not to, I mean, that's a real life example with like the secretary thing. Let's say that you call to the secretary and rather than, because typically if you call up like Verizon, call up AT&T, you know, you're going to get, you call the 800 number, you're going to get like their top level thing, and then they're going to transfer you someplace else. And that top level number is not going to have a busy signal, right? You're going to be able to call, somebody else can call in right at the same time, and they kind of get put in the queue to be dealt with. All right, so that's kind of what's going on here. But, you know, if you're dealing with a small business, let's say you're calling a lawyer in Grafton, you know, small boutique law firm or something, there's a possibility that when you call, you're going to get a busy signal because they're dealing with the current customer that called, and they don't have a system that allows them to send that off to somebody else to deal with. So the same thing would be true for writing the software. If you wrote this software in such a way that it did not create the child processes, then it would stay busy. You have a question? Go ahead.
I was just gonna say, once the thread is terminated, it gets back to the person that made access.
Well, the thread would get terminated when you leave the website. You know, like, hey, I'm done with you. You know, if you're calling customer service somewhere, you know, you have a connection directly to that person's desk for, you know, the 3 or 4 minutes you're talking to them. And as soon as you're done and they hang up the phone or you hang up the phone, whoever does it first, that's going to break that connection. That's probably going to end this process. Or we have these things in some modern software applications, sometimes called thread pools, where you pre-create maybe, I don't know, let's call it 500 threads. Okay, so they're already generated. You just say, look, this operating system, it's this computer, its entire job is to solve this web server problem. It's all it does. So rather than only create helpers when an incoming connection comes in, which could take, a little bit of time, it would add up to real, meaningful time if you had 10,000 people all hit the server at the same time, and then the operating system had to spawn a child process, spawn another one, spawn another one, spawn another one, all at that same time. Then you start feeling it as a person. I think we talked about like IO is slow, right? So if we just print out one thing, it seems fast. If you print out a million things, the program takes a while to run. So with that in mind, some software applications pre-spawn their child processes or their threads. So they're just sitting there like they're a football team ready to jump into action, right? So whoever's I'm next in line. So when the incoming connection comes in, he's just ready to go and he helps. Kind of like when you walk into Best Buy and they won't leave you alone. It's kind of. All right. Other questions so far? Okay. Now, any way you cut it, regardless of how the infrastructure is built here. So this is all dealing with, we're dealing with systems programming here because we're deciding, what is the mechanism I'm going to use? How am I going to leverage this operating system to pull off the magic trick of talking to more than one client simultaneously? You're still going to be at the mercy of what the hardware in this web server is, the actual computer hardware. Is this a single core Raspberry Pi that can actually only do one thing at once, but just does it really, really quick so everybody's faked out? Maybe. Could that handle 4 concurrent users at once? Probably. Just speaking HTTP, and the end users wouldn't know any different. But chances are, if you're connecting to like Google's web server, which is actually probably just a front man for a server farm sitting behind it, which is going to hand off your request to the actual single computer that's least busy right now out of the 5,000 computers they have at that location, when before that you were actually routed to the regional location that was fastest for dealing with you. So there's a scalability situation here. They can handle more simultaneous connections at once. That's reliant on the hardware. That's something that the software we write can't fix, right? We could say, hey, I just wrote this software that's going to do some stuff with processes. We're going to be doing some system software, system programming stuff where we're talking to the operating system. And maybe we're not going to pre-create 5 million processes if we're running on a single core Raspberry Pi with 512 megabytes of memory. That might not cut it to create a million processes ahead of time. Maybe you just do a first come, first serve and just say, hey, this is just we're prototyping this, this isn't production ready, that type of thing. All right. So this would be how a web server generally works in terms of the communication. These web browsers all talk to the server hands them off to individual computing units so they can all be dealt with at least pseudo at the same time. Probably, since this is only 4 in this case, there's probably 4 individual processors. So they actually are being dealt with at the same time, or at least it's plausible they're being dealt with at the same time. And what's being spoken across this is HTTP. That's the language. That they're speaking. All right. So HTTP is a relatively simple language, and this is where we're going to wrap it back to RESTful APIs here in a minute. Okay. So HTTP, for instance, probably the most common HTTP request. If I go into my browser and I go to www.weather.com and I press enter, it just established a connection to weather.com's web server, which then spawned off a thread to talk to me. And then over that thread from this web browser, I sent a GET request, G-E-T. I said, give me the website that is very likely index.html. Oh, it's actually not index.html, maybe home.html. No. Index.htm. Index.php. Oh, who knows what their back technology is. But anyway, you cut it, when they hit it, it's going to, we're going to say, get me your home page. And the web server software is going to be set up to, by default, serve a certain page. Historically, it's usually index.html, or for dynamic pages, it might be index.php or index.asp or ASPX, whatever. All right. That's what the web server will serve by default if you don't ask for a specific page. If I go to hourly here, let's see what, so now you see that it's actually asking for a little bit more. It's asking for, you know, the weather directory inside that, the hour by hour directory inside that, some other stuff. And then it has this unique code that was part of this request for security reasons. All right. But at the end of the day, we are speaking the HTTP language, and my web browser is asking this web server to give us an HTML document, give us content. Okay. And we're doing that using a GET request. Put it on here. HTTP functions. We have GET. Anybody know what other functions HTTP supports? Go ahead. Post. What is one? One more. Go ahead. Nope. Go ahead. One more guess. Go ahead. Delete. All right. So now this is where it becomes interesting. Now, how long has HTTP been around? Beginning of the internet? Day one, when the internet was being used by consumers, the first thing we did on the internet was do web browsing stuff. We were on the World Wide Web, right? You know, and our browsers were speaking HTTP since day one. So we're talking years, 35, 40 years since HTTP was probably created initially. But we've been actively using it for well over 30 years. Okay, so certainly nothing new. And HTTP is very simple. It knows how to do four things. GET is used to request a page. Post is used to send. Well, here, we'll do it this way. Send new info. Don't worry about that right now. Put is rarely used. And so is delete. So actually, as simple as it is, it knows how to do four things. Our common uses of it only use half of those abilities. when our web browser is talking to an HTTP-based web server, which all web servers are going to be that, it's doing everything through gets and posts. When your web browser wants a page, it's going to be doing a get. When it needs to send information to the server, it's going to be doing a post, but it can also send information with a get. It's just a different way of sending. It's a less secure way of sending information, or a less obvious way. Secure is probably the wrong term. It's a less obvious way of sending information. But in any case, HTTP knows how to do 4 things, and we only actually do 2 of them with our web browser. And it's been around for forever, HTTP. So we talked about this idea of CRUD. Create, replace, update, delete. All right, so this is what this guy means. The idea is that when our program talks to a API server, everything we might want to do falls into one of these 4 categories. Make sense? I want to create something new. I want to replace something that's already up there. Actually, replace is the wrong. It's not replace. What does the R in CRUD stand for? Update is to replace something that's already up there. Yeah. Create something new, read from the server, update something that's already on the server, or delete something that's on the server. So the idea is that all of the API servers, anything that we might be talking to, everything we want can be represented in these 4 things. Hopefully you kind of see the direction we're going here. 4 exact things we might want to do when talking to an API, this idea of CRUD. So when we talk about RESTful APIs, these are CRUD based. Use the HTTP protocol for all communication. So the read is a get. Create is a post. An update is a put. And a delete is a delete. So if you are asking the API to give you some information, you're going to be sending it a GET request. You're asking, if you're saying, I want to create something new and have you store it in your data, it's going to be a POST request. If I want to update something that's already in your database, let's say, I'm going to probably send you some JSON with the new information. I'm going to send it in the form of a PUT request. If I want to get rid of something that's already up there, I'm going to send it in the form of a delete request. All right. So even with the same endpoints, you could have an endpoint just called do something at weather.com. And depending on which function of the HTTP protocol you call that endpoint with, it will have different responses potentially. It'll have logic written for a do get. It'll have logic written for a do post, a do put, a do delete. It'll have logic for those different things. Go ahead. See, are you saying just generally speaking, if we're working with APIs out there in the wild, a majority of them that we might work with as consumers of an API, we're probably going to be doing a high level. We're probably going to be reading most of the time because we're probably looking at getting information from them. But going back to the example we used earlier in class, when I said, well, what if you work at weather.com and you're writing internal software, you might be using that same API to update the database. You might have everything flow through the same central API rather than talk directly to the database. That way you can control the logic of, hey, let's make sure we can ask a question about what he's trying to add to our database or what he's trying to delete from our database or update in our database. Let's not let him just do it directly. Make him go through the API so we can possibly flag it as suspicious of something weird's going down. All right, so I mean, I think your question's a good one, but the answers, it has got a couple different answers, right? For us as consumers, we probably are usually using an API to get some data. But that doesn't mean that APIs aren't very commonly used to do all four of these things. Okay. But now the interesting thing with this is our latest, greatest, coolest, most modern based APIs called Restful APIs, which just sounds quirky, smart, I don't know, sounds something, are actually based on HTTP, which has been around since the birth of the internet. Rather than like SOAP invented a different standard, rather than utilizing a standard that's been around for a long, long, long time. So we're hiding super old technology under a term that is not brand new. Restful APIs have been around for a while now, but it's our current standard. Again, why fix it if it's not broken? But why are they called REST APIs? Yeah, it is. We can look it up. Representational state transfer. It conforms to the constraints of REST architecture style and allows the interaction with RESTful web services. REST stands for Representational State Transfer and was created by computer scientist Roy Fielding. Yeah, it's not even a good acronym, right? Because the first two letters deal with the first word. But that's what CS people do. I mean, when you took your, you probably first started talking about it in your 250 class when we started talking about design patterns. You said one of the, you know, you got this idea in technology, or idea in education, but, you know, we deal with it in computer science. Publish or perish. So we have to be doing scholarly research, you know, and a design pattern is a proposed good, you know, good solution to a common problem. Well, what's a common problem? What does it mean to be good? So all we have to do is come up with an idea of a way of doing something and give it a crazy name. Like we looked at singletons. We looked at MVC, model view controller. But, you know, representational state transfer, you could have just called that REST and just gave it a name, and I'm not sure that these words actually mean much anymore. All right, so questions about that stuff. All right, so purpose of this, we kind of just talked about how does the internet work, but the purpose of that lecture wasn't really how does the internet work, even though it hopefully was somewhat instructive. It was really more about this slide right here. How does systems programming actually work? This is a client program. Doesn't matter that we were using web browsers as our stand-in. This is another program that's acting as a server program, but effectively these are just two computer programs that are talking to each other. Inter-process communication, IPC. So these are two separate programs, two separate processes that in our world probably live on different machines. But I know you guys do it in the, how many of you have had the database class, 430? I'm pretty sure in there, doesn't he have you load like a PHP based web server on your computer? So you're running this web server on your computer, and then you're creating a web page in your browser that's talking to that local thing. So you're not actually talking over the internet. You have a program, the web browser, that's sitting on the same computer as the web server, and they're talking to each other. Make sense? So this doesn't say anything about where these programs live, but these programs are talking to each other in some way. Okay, and they have to use a mechanism for doing that. And what it's using is it's establishing that phone call through something called a socket connection, which is done over a TCP/IP network connection. And then we're communicating in the language called HTTP. All right. So, purpose of these guys talking about an API is when we talk about these things called system calls in our operating systems, it's fair, I think, for us to think about system calls in terms of them being the API that our operating system provides. Okay. Now, where it does deviate some from an API in the simple terms that we've given it here with the CRUD, that stuff, is that when we talk about system calls, these are really programs that go and do something for us. And it's not always about creating something new or reading something or updating or deleting. Sometimes it's just doing our bidding. It's just running another program. Could be creating a file, which would fit into the whole CRUD thing. But system calls are typically programs that do something on the current operating system. And those guys fall into a couple of categories here. So process control, and that's what we're going to be talking about quite a bit. File management, device management, information maintenance. This would be like logging and stuff like that. We probably won't talk much about that. And then communication, typically between processes. All right. So these are the collection of things that an operating system provides to the programmers through an API, through libraries, an interface for talking to the operating system. And I would say that all operating systems are going to share some of these system calls. We've seen it when we looked at the Hello World in Linux. We saw that the compiler targets two things. It targets an operating system and it targets an architecture. So when it was talking to Linux and it wanted to write something to the screen, it was targeting the syswrite system call. That's the system call that knows how to write something to the system, right? And that system call needed a couple of pieces of information. It wanted to know, what do you want to write? How long is it? Where am I going to write it? A couple different destination choices where you can write it. Maybe you're going to write it to another file. Maybe you're going to write it to the screen. Maybe you're going to write it to dev null, which is like into kind of just float it out to the nether. So it has a destination and then a what associated with it. All right, so this is going to kind of introduce some of these system calls that we're going to be talking about in here. And the first one we'll probably look at is the fork system call. You maybe have heard me reference this before, but effectively, these are not an exhaustive list of system calls, but for the process control system calls, here's three common ones. Fork is the C-based system call in Linux for creating a duplicate process. So if we kind of go back here, this example, I said thread or process. Threads would be the newer way of doing it. The fork keyword creates a new process, which is considered heavyweight. And we'll talk more about that. Well, actually, that's actually your homework assignment. So actually, let me write that down real quick, just so I don't forget it. I don't know. So research threads versus processes and tell me the difference between them. All right, because that's an important distinction, and we're going to be looking at both of them in here. So I'll get the ball rolling for homework assignments. But the fork system call literally creates a duplicate of the current program. So you have a brand new, completely separate process. And that'll make some sense what the pros and cons of that are once you do your research, and we'll talk about it more next class. Some words of wisdom: when you use the fork system call, make sure you fully enunciate. It is a dangerous word that if you say too quickly can sound like other words. There was a very interesting conversation that I had when I used to be a Unix system administrator years ago, and me and some colleagues were sitting at this restaurant for lunch, and we were talking about, so when you use the fork system call, the result is a child process. So while we're at the table talking about things, we're talking about forking children, and this lady nearby was getting very upset. And one of the other guys was talking about the program he wrote called Reaper, which was reaping children. So yeah, it's an unfortunate system call name. But what's interesting is it's now persisted. Several of you see it in online GDB, which we'll use in here, but you've seen it in GitHub. When you are using one of my starting points, you usually fork my repository, right? So you make a duplicate, and then from that point forward, it's its own thing. So this system call has persisted throughout our world. It's actually a Unix system call. It's been around for a long time. You know, and it makes sense where the word comes from. It's like fork in the road. Okay, when it splits right there, and at that moment, they are literally duplicates of each other, but one of them is the clone. And we'll talk about that next class. How do we see the clone? We'll start writing some code with it. So it's actually quite easy to create a duplicate process, but the logic that goes along with, okay, am I the original or am I the clone? If I'm the clone, maybe I have this set of things I'm going to do. If I'm the original, maybe I go back and listen for the next phone call. For example, if we use our web server example here. All right, other common system calls: exit. Program is done. Tell the operating system to kill off this process. What does that mean? It means reclaiming all this stuff, the memory associated with it, get rid of the process ID so it can hand it to somebody else. But at the end of the day, from a programmer's perspective, we want the current program to end. So we're saying exit and let the operating system do the heavy lifting, whatever that means, to have a process fully exit, okay? And then exec is executing another program. So we can tell our operating system to actually launch another program, which probably would then also result in another process, but not necessarily a duplicate of the current process where we have control over what happens. It's another process that is another program running on the operating system. All right, makes some sense? Similar, file management. We have the ability to open a file, to read a file, to write a file, to close a file. Device management. This is the tool that you interact with the driver manager of the operating system to you kind of write a program that has a couple of different functions for what happens when you first load the driver. What happens when this general thing happens? What happens when this other general thing happens? So this associates a driver with the current running operating system. So information maintenance, this really deals more with, I would call this process management. So get PID, this returns the unique identifier from the operating system's perspective of the current process that's running. So if I'm a program that's running, I have a PID. I have a unique identifier according to the operating system, a number. And my PID is going to possibly, especially when you're dealing with the fork system call, when we create a clone, the original is going to have a PID and the clone is going to have a PID, and that PID will not be the same because now we have a brand new process that's running. Make some sense? So it might be handy when we're writing code for a process to be able to tell you what its PID is called. Because we might want to, maybe you have, in this example, maybe this program who spawned off a bunch of child processes, maybe he's in charge of killing off the children once they're done doing their job. So this child might report back to the parents his finding, say, hey, here is the information you wanted me to go work on. And the parent says, thank you, zap. Okay, now it's dead. We reaped the child. It's the idea. So these are kind of the things that we're going to be messing with in here. So for next class, take a look at the difference between threads and processes. We'll talk about that to start class, and we'll probably start looking at actual code on Thursday. Questions, comments, concerns, bribes? All right, I will see everybody on Thursday.